only this group because none of you have the warm-up done.
I'm sorry, I was hungry.
I did really good on my other test, though.
Yes.
How did I do on my retake?
You did great too.
Did I?
Yeah.
What do you get?
What did I get?
It's in Canvas.
Is it?
That's bad. It's the confidence. The mom of
Yeah. Maggie, you're supposed to be copying this down.
What?
Can I read everybody my fortune?
After you copy this
Okay.
down.
I have an 11% right now. That's a good.
I'm at 24.
I have 8
So-
fellows.
Tori.
You're 8% in the class.
Because I didn't do the test.
I answered the multiple choice questions, obviously.
So I'm 0 out of 100 on some of it. Which is rough.
It's rough.
I know. I might have to take that test at some point, right? Little.
Yeah, it'd be just a shame if this class just disappeared.
God, that would be a crime shame.
Oh, thanks. Don't look at me like that. You didn't do
Corky
this.
says,
Maybe I'll take back the retake score.
No, you can't do that. That's
Yes, I can.
That's actually
How is
not
it?
allowed.
he says, sorry, Brooke, I thought Jeremy had already messaged you about training. He's in here just a couple hours. I was checking him and get back to you. Hey. Why did he say hey? Oh, he's very stupid when he texts.
Like, look at this.
This is semester 2. Semester 1.
Thank you, sir. All right. Population is the 12,000 guys from the University of Illinois. The mean is 7.11. Standard deviation is 0.74. Then they took samples, and the mean for the sampling distribution was 7.11. And the standard deviation was 0.074. And the only thing that changed is our standard deviation is lower.
Why is it lower?
Because we divide by the sample size. Actually, we divide by the square root of the sample size. And the square root of 100 is 10, so we move the decimal.
I got you.
No, I'll email in. All right, so
Never mind will lead you to many rewards. That literally
That's
happened
what
today.
just happened. That's what just happened.
all right, so we are gonna play with some Reese's Pieces today. I totally am very sad, but this is, unless I didn't go to Costco, but this is the biggest bag of Reese's Pieces.
Let me guess. There's no orange pieces.
Wouldn't that be crazy?
That would be crazy.
So I had to buy 3 bags so that we had 1,000 pieces.
Why didn't you go to Costco?
That's one of my other bags. Because I didn't have time to go to Costco, and I don't know if they sell them, but that's where I would think you could get a really big bag. But these were the biggest bags.
Window is.
They do more like individual stuff. I feel like Costco, you have to get a big party bag size of like different kinds of chemicals.
Well, this will work for today.
get to eat
Next
them.
time, after we do our activity, next time we play with Hershey Kisses. So I'll have to look at Costco. It's right around Valentine's Day too. I didn't do that on purpose, but it worked out. All right. So we're gonna play with Reese's Pieces. My 3 bags, we're gonna say, is one big bag that has 1,000 pieces.
Okay.
You can actually look up on the manufacturer, the Mars, and what's the other, Hershey's? You can go to their websites and look up the distribution of the colors. And the distribution is that 40% of Reese's Pieces are orange. So we're going to take a sample of 50 pieces.
Is that a lot?
X is going to represent the number of orange candies. So what are all the possible values for X?
a lot.
0 through 50, because there could be, that random bag that has none of one of the colors. So we could have 0 orange candies all the way up through 50 orange candies, right?
Thank you for the applesauce, Miss Whittle.
You're welcome. What kind of distribution are we working with? Think back to chapter 6. What were the types of variables we worked with?
discrete and
Continuous,
Yes.
and what else?
I don't know what the one.
That explains it.
I've never heard of this in my life.
oh my god.
Pay more attention.
What's the third one?
There's 3 others that we did.
Wow. Okay. I wish Ali and Dia were
Starts
here.
with, I know, me too. Starts with an N, B, and a G.
It's
Fine.
Big.
Binomial is one. Geometric is another. And then normal. So, which of those, binomial, geometric, or normal, are we... Try again.
Oh, for one.
Try again.
Geometric. Damn. Binomial.
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 Done.
1 for 3.
All right, so it's binomial.
Why is it
So,
binomial?
well, we're going to do our little checklist, which DJ bins.
I do know that.
Okay, so what does the B stand for, Colton?
Success.
And
Which would be, I don't know.
success and failure. Orange and not orange.
Okay.
So success is orange, failure is not orange. What is the I?
Independent.
Independent. Now remember, this is one of those where we're just going to assume so we can go ahead with our problem.
So we're gonna put each one.
You're going to say it's independent or not?
Assume independence. Because our population of 1,000 pieces is so big,
Oh, yeah.
it would change it just slightly so we can assume independence. What does the N stand for?
Where's it without?
It's like
Number. And what's our sample size?
50.
50. What's the S? Success.
0.4.
0.4. Probability of success is 0.4. Anybody remember the formulas for mean and standard deviation of a binomial?
It's mu p, and I got nothing.
Okay. Anybody else want to
It's
try?
mu is np.
Mu
and then I don't
is
know what
NP.
I don't know what the sigma is. They're really good.
What's the standard deviation?
It's something with the square root thing.
It is something with the square root thing.
Is it SX?
your net.
No.
NP times 1 minus P. Yes, S sub x is a way we write standard deviation sometimes.
So you never know when you're
So, N is 50, P is 0.4.
what?
Maggie.
90.
So 40% of 50 is 20. So we would expect in our samples that there are 20 orange ones. And then our standard deviation. By the way, 0.4 is what percent?
40.
40%.
Do you know how many of you messed up on chapter 6 because you made 6 or 7%, 0.6 or 0.7?
Oh yeah, I've done that a lot of times.
Oh my gosh. So many of you.
But I learned.
I've never done that.
So many of you.
But
Yes.
Can we throw away stuff from the past? Like notes and stuff?
Are you happy with your grade?
Of the past quarters?
Yeah. Wait, thank you, ma'am.
Yes.
wow.
Yeah, sure. Although, I have had students hold on to them, and then they go to college, and they tell me those notes are more helpful than the notes of their statistics class in college. All right. 50 times 0.4 times 0.6, and then square rooted is 12, and the square root of 12 is 3.464. Everybody good with those? You better say yes.
Yes. You can flip the page.
Thank you. All right, so how do we draw a probability distribution? with a pencil.
Yes.
A bar graph, yeah.
No,
Isn't it the dot plot?
No, that's for a sampling distribution. This is for a probability distribution.
Box plot.
Do you guys, no, not a box plot. Mason was the closest with the histogram, but
Bar graph.
remember last chapter I told you that sometimes we can use a normal curve for non-normal variables if we check two conditions. Anybody remember those two
remember that.
conditions?
What's right here?
Boo.
This owie. This owie. This owie. This owie. This owie. And this owie.
Can we use a normal curve?
Freebies.
Well, we need to see if n times p is greater than or equal to 10, and n times 1 minus p
He doesn't do the whole
is greater than or equal to 10. N times p is the number of successes, so how many orange candies can we expect?
50, right?
Our sample size is 50. We can expect 20. That's our mean. Is 20 greater than 10?
Yes.
Okay.
I think so.
And then the other one is our number of failures. If we expect 20 to be orange, how many can we expect not to be orange?
30.
30. Is that greater than or equal to 10?
greater than.
So can we use a normal curve?
Yes.
So let's use a normal curve. We can draw our probability distribution. We've got the normal curve.
How do you?
I've been teaching this class for 8 years. I should be able to draw normal curves pretty darn well.
Oh, you ate that.
Mine's kind of awesome too.
We have
Mine's not that awesome.
20 at the middle.
So did you cook him in chess? Always play chess.
Yes, they do. Drives me insane.
You chess.
I don't know what that is. We'll go with 26.928.
What?
That's 30 something. I should actually add them. 20 plus 3.464 plus 3.464 plus 3.464. And then we can subtract 20 minus that again, decimal like that, minus. All right, so we have 16.536, 13.072, and 9.608.
I actually do remember that.
So then I could ask you to find the probability that you get 28 or more orange candies in your sample, or I could ask you what's the probability you get 17 or less. And we would use normal CDF to find it, right? But we've already learned how to do that. So we're going to change things up. And instead of being concerned with the number of orange candies, we're going to be concerned with the proportion of orange candies. So how do I take the number of orange candies and turn it into a proportion?
The number of orange candies.
Number of candies over total.
And what's the total?
50.
50. So really we divide by our sample size, right? So in a minute, I'm going to come around, give you guys approximately 50. Oops, sorry.
Where are you getting more?
After you count them and find the proportional orange, yes. I'm pretty good at estimating, but first thing you're going to do is count and make sure I gave you 50. If I didn't give you enough, let me know how many more you need. If there are extra, just eat the extras.
Oh well.
Okay?
Yeah, definitely.
Once you make sure you have 50 Reese's Pieces, then you need to count how many of them are orange and turn it into a proportion. So, if we were to take a sample of 50 candies, which you will in a minute, and we're looking at the proportion, what proportion do we expect to get?
What proportion do we expect to get? 0.4.
0.4.
20 out of 50.
20 out of 50, which when you divide by 50 gets you back to 0.4. Now, are you all going to get 0.4?
No,
Why not?
because we're getting different candies.
We're gonna SRS.
Different samples. It's called sampling variation. So, like I said, I am going to come around, give you, and I'm going to estimate 50. Make sure you have 50, then count the number of orange.
Oh no,
Now, I don't have any Kleenex, unfortunately. Otherwise, I'd give you a Kleenex to dump them out on. If you're okay dumping them out on your paper,
I'm okay with that.
otherwise, I do have a few paper plates if you would rather do that.
I think we should all eat off the desks.
How do you get the rest of the bag?
May I flip my paper?
Brooke brought 'em over here. No, I don't. I was talking about Reese's.
All right, so we're going to go around. You guys are going to tell me your proportion of orange. We're going to write everybody's down so that we have a somewhat good sampling distribution, but with Allie and Dia gone, it makes the class really small.
Huh?
I miss Allie and Dia.
Go with me.
You're here. How could I miss you? All right, Colton, let's start with you. What was your proportion of orange?
26 out of 50. So that would be 0.52.
Thank you, sir. 0.52. DJ. Brooke.
Mine's 0.4.
0.4.
You're a liar.
Sam.
0.6.
Maggie.
1 second.
Megan.
0.52.
Clara.
0.4.
Amber.
Wait, is it orange out of
Yes, orange out of 50.
30 out of 50, so
Point.
6.
0.6. Thank you, Mason.
0.5.
Ethan.
Also 0.5.
Maggie.
0.64.
Whoa.
0.6.
0.64. All right, so now we're going to make a sampling distribution. We are going to make another graph in a minute, so draw a line down the middle so that you have space for two graphs.
Do you want my data, Miss Rule? Because I haven't.
Did you have 50 in there?
50? No.
Well,
Isn't
then-
she at 50?
Then no, I don't want your data. Thanks, so. All right, so we're going to make, on the left, we're going to make a graph for the class's sampling distribution of p hat. Okay, is it just an apostrophe or an apostrophe s for classes? I always get
EF. EF.
Yes.
no.
It's apostrophe S, because
Oh, like-
classes and both.
It's ownership, so it's S apostrophe.
If it was
Right?
if it was apostrophe afterwards, it would have to be classes. As a
Thank you. That makes sense. All right, so it's the class's sampling distribution of p hat. Excuse me, that we're going to make over here on the left. So our lowest was 0.4, our highest was 0.64. So why don't we go 0.4 to 0.7? So we have a little, well, yeah, 0.4 to 0.7 works. So 0.4, 0.7, which means I need 0.5 and 0.6. And then I'm going to put 4 hash marks in between each of those for the 2, 4, 6, 8 of the decimals.
Oh, it's so cute.
And then we're going to put points for each of our samples. So we have 0.52, 0.54, 0.4, 0.6, 0.52, 0.4, 0.6, 0.5, 0.5, and then Maggie. That's a hideous graph. Oof.
What about Maggie?
So we have 3, 5, 7, 8, 9, 10 people in class, so I should have 10 points. 2, 4, 6, 8, 10. Yes. What's going to be the center? Which dot or dots are we looking at to find the center?
5th and 6th.
5th and 6th. Because 10 is even, there are 2 middle dots. 1, 2, 3, 4, 5, 6. So we are centered here at 0.52.
Oh my gosh, that's me.
That is you. So, thinking back to yesterday, do we have bias?
Huh?
Do we have bias?
Yes.
Yes.
Did we overestimate or underestimate? We overestimated because remember it should be that we're around 0.4. That's the parameter. So we overestimated. Would you say high bias or low bias?
High.
High. We're pretty far away considering that we're working with decimals.
What would be considered low bias? Like
0.44, 0.38. We're close to 0.4, but we're pretty far away. What about variability? High variability, moderate, or low? Variability is spread. Doesn't really matter where 0.4 is. Do we have a big spread, a medium spread, or a low spread? Big spread. 0.64 to 0.4 is 0.24. Yeah, it's like, I mean, we could have 0 to 1, right? And we have 0.24, so it's almost a fourth of the spread we could have. So high variability. Now, I have a statistical applet that takes samples of Reese's Pieces that we're going to look at. Bear with me. I forgot to pull it up before class, so I gotta do that really quick. That's not what I wanted. Oh, no, I was right. I do want to be in there. All right, look at the cool little Reese's Pieces machine. Look at that. Isn't it cool? All right, so probability of orange, 0.4. We wanted to take a sample of 50. Now, on your paper, it says we're going to do 500 samples, but I just have to show you. Look at this. This is cute. But before that, I have to change it to proportion. We're interested in the proportion. And then I'm going to tell it to draw a sample. And look, it sorts them. And I love how the little pieces just move. Sorry, I'm weird. I find statistics happy. So that sample had a p-hat of 0.46. So that means what? 23 of the 50 were orange? All right.
Find stimulation.
Who
Why is this a thing?
Who's like, I wonder. Who's like that big?
99 samples at once. So we have 100 total samples. fun.
Is this just random or is this like?
Look, the last p hat was 0.28. So that means they only had 14 orange out of 50. Now your notes say 500 samples. We have 100 so far, so I'm going to jump and do 400 at once. All right, so we have our 500 samples. I'm going to click Summary Statistics. It tells me the mean is 0.403 and the standard deviation is 0.068. So we're going to make a little sketch of this on our paper. Our lowest p hat is what? 0.16? Does that look like 0.16 or 0.18? I think that's 0.18. Yeah, it's a little past the 0.16. And then 0.58. All right, so we're going to make a little sketch. So I got shocked. My little metal thing here. All right, so 0.16, and it was 0.58. So let's go 0.1 to 0.6 for this one. 2, 3, 4, 5. So I need 4 in there. 2, 3, 4, 5. And then we're gonna, we don't need all the little hash marks because, well, it's just gonna be a sketch. The lowest one was 0.18, excuse me, and the highest was at like 0.58. And then our mean is 0.403, so it's going to be centered around here. And then we had a little shorter, and then it got a little higher again. And I'm drawing the picture from the computer, but I can't show both at once. Are you okay, Maggie? Oh my goodness.
No, you need to look at this.
Oh.
It's okay. This is gonna be really good.
Alright, so it looks something like that. This is the Java applets sampling distribution. So the applets sampling distribution.
Oh, chill.
And we were told the mean was 0.403, so centered at. So, do we have bias with this sampling distribution?
Very low, but yeah, I guess.
Yeah, it's not exactly 0.4, but it is really, really close. So yeah, let's go with low bias. What about the variability?
High variability.
Yeah, it's actually got a bigger spread than we had, right? 0.58 down to 0.18 is 0.4, and ours was only
Wait, but I thought we said
0.25.
yesterday that more samples lowers the variability, but stays.
Bigger sample size, not more samples. We still just did a sample size of 50. We would have to increase the sample size to decrease variability. But that was a good question, Colton.
That's a good question.
Nice try, Colton.
All right, so mean
Biggest golfers.
and standard deviation of p hat. Instead of looking, Maggie, at the number of orange candies, we switched to look at the proportion of orange candies, which means our formulas change. So, before, when it was binomial and we were looking at the count, we found the mean by taking n times p and the standard deviation by taking n times p times 1 minus p. Then Caleb.
Yes. Sorry.
Then we said, okay, that measures how many successes, the number of successes, but we're interested in proportions. So what did we do to turn the number into proportions?
Number divided it by the samples.
Divide by our sample size.
What's the difference between sample and sample size then? 'Cause I'm getting
One sample would be like what you did. That's one sample. Your sample size was 50.
Okay.
So when we divide by n, our sample size, what happens to our formulas? So if I take the formula for mean and I divide by my sample size, I now have an n on top and on bottom that cancels out. So the mean of p hat is just p.
Parameter?
Should match our parameter, which makes sense, right? If we have low bias or an unbiased estimator, it's going to be what our parameter is. For the standard deviation, same thing. We're going to divide by the sample size. I could go through all the algebra to show you why, if you want, or you can just trust me that it becomes the square root of p times 1 minus p over n, and all of that is under the square root.
Okay. You know, yeah. I
So,
agree.
the mean for p hat is p. In words, that means that p hat is an unbiased estimator of p, our parameter. The standard deviation of p hat is the square root of p times 1 minus p all over n. And all of that's under the square root. Now, there's a little caveat. That's how you say that, right?
Well, what?
Caveat.
What is that?
There's a little,
It's a catch.
thank you, catch.
Oh.
Thank you.
There's a catch. We can't use that formula unless the 10% condition is met. And the 10% condition says that our sample size has to be less than or equal to 1/10 of the population. Little n, sample size, big N, population. Maggie, are you writing this?
Are you ready?
Yeah, I am
You
reading
wrote it
this.
all down.
It's all written
Oh, you
down.
actually did.
Yeah.
I was being sarcastic.
You have nothing written down.
Yeah, I do. I did the graphs. Graph.
Wow.
So now we're going to go back to finding the probability. We're going to use a normal curve. May I flip my paper over?
Yes. Good look at word.
All right, so our bag of Reese's Pieces contains exactly 40% that are orange. If we select, by Tori, if we select a random sample of 50 candies, what's the probability that a sample will give a result within 2 percentage points of the true value? So first of all, remember back here, we checked those conditions so that we can use a normal curve. That still holds true. We're just going to recopy them so that if you just look at this example when you're studying for a test, you remember that you have to do these. So to use a normal curve, we have to check n times p is greater than or equal to 10. And n times 1 minus p is greater than or equal to 10.
First C2.
NP is 20. That's greater than 10. And n times 1 minus p would be 30. That's greater than 10. So like I said, we already checked that. This is just a reminder. If you were to study this example only, you do need to check that. So then I need to know my mean and standard deviation so that I can label this curve correctly. And we just learned the formulas for the mean of p hat. What is the mean of p hat?
It's just P.
It's just p. And what is p in this case? 0.4. 40%. That's our p. And standard deviation of p hat, that's the square root of p times 1 minus p divided by n. But what did I just tell you? We have to check before we can use that formula.
What? It has to be less than or equal to 1/10 of the something.
So to use this, we have to check that the sample size is less than 1/10, less than or equal to, 1/10 of the population. So our sample size was 50. What was our population size? 1,000. Thank you. That was way back at the beginning. I told you on this page that a big bag contains 1,000 pieces, and that the store I went to didn't have a big bag, so I bought 3 small bags to make a big bag with 1,000 pieces. Is 50 less than or equal to 1/10 of 1,000? What's 1/10 of 1,000? 100.
So yes.
So yes. So we can use our standard deviation formula. So we're going to put 0.4 times 0.6 divided by 50 and then square root it. And I did not leave much room, sorry. 0.4 times 0.6 divided by 50, and then all of that square rooted. 0.4 times 0.6 divided by 50 square root. So 0.0, we'll go with 0.07 just to make the number easier when we label them. So 0.07. So I have a mean of 0.4, standard deviation of 0.07. So now I get to label my normal curve. This will be 0.47, 0.54, and 0.61. That'd be 0.33, bless you, 0.26, and 0.19. Yeah.
What? I did that.
They also made us used to actually learn our facts. I guess because I have kids in the school system now, a calculator shows up on the school supply list, if I could speak, in first grade. And I absolutely refuse to buy my children a calculator in first grade. That's when they should be learning mental math and how to do things instead of learning how to press buttons on a calculator.
I didn't get a calculator until 5th grade.
My oldest, he got really angry in 7th grade. He was like, please just give me a calculator. I hate always borrowing one from the teacher. I'm like, fine, but don't use it.
Fine, but don't use it.
All right, so the probability that we need to find. what is the probability that our sample will have a result within 2 percentage points of the true value? So first of all, what's the true value? What's P? 0.4. So within 2 percentage points. What's within 2 percentage points of 0.4?
6.2.
You guys just did what I said you guys did on chapter 6. 2% is 0.02.
0.42 and 0.38.
0.42 and 0.38. So we want to know what is the probability we're between 0.38 and 0.42. So 0.38 is, we'll say there-ish. And 0.42 we'll say is there-ish.
What if I
Just tell her.
And we want to find the area in between.
What would you do if I just said?
What's my calculator function?
Normal.
Normal what?
F.
CDF. What's the lower bound?
0.38.
Upper bound?
0.42.
Mean?
0.4.
And standard deviation.
0.07.
And that, I guess I should have put first, just to put it in math terms, is telling us the probability that X lives between 0.38 and 0.42. If you were to see that in a problem, that's the same thing as what those words are asking us. Did anybody do it in their calculator? Colton Morgan?
I did not.
Why not?
I'm lazy.
Stop being lazy.
Brooks' calculator is dead.
calculator is gone. I also forgot how to make
Well-
distribution, normal CDF. I got you.
Okay.
Got you, Kev.
0.38, 0.42, 0.4, 0.07.
2.5.
Yeah, it should be 0.225. I heard 0.25. I was like, so we get 0.225. So, last thing, one more thing to listen to. What does that tell us?
That means that the sample.
There's a 22.5% chance of it falling between 0.38 and 0.42.
Thank you. I'm going to put a little more context in there.
My whip boy.
About 22.5% of the time,
Oh, you can scan or you can print that.
our sample
Can you duck me, boy?
will
You had a boy.
be
Wait,
between
I'm sitting at the gym. I'm sitting at the joint.
0.38 and 0.42
Do you want me to sing it?
Yeah.
for the proportion of orange candies. And then he wonders why his test score is so low. Bruh. Bruh.
I just accept.
Questions?
Let's go.
Can I go study in the library?
Stink eye. Every time
No.
you look at me like the past 3 days.